and that would be the critical value. I hope that helps, Matthew and Chicago. All right, here we've got the same problem. This is based on flexure, topic of flexure, and we're talking about shear stress in bending. Specifically, they will say this, shear stress in bending. So as soon as you hear that terminology, remember the equation that you need is this equation. And a lot of people, for some reason, and I will explain some of the reasons that I think may be contributing to this, but a lot of people have difficulty using this equation. All right? So please pay attention and try to see if you can learn this. Remember what we're doing. We're calculating the shear stress in bending. All right? Now, the equation, as I said, is VQ over IB. By the way, shear stress, we always use the Greek letter tau, T-A-U, tau. And that's what the symbol looks like. So tau is equal to VQ over IB. I want you to understand the ingredients that go into this equation. Starting from the numerator, V. V is the shear force. So V is the shear force, and that we get from the shear diagram. All right? Q, if you don't mind, I'll get back to Q in just a minute. Denominator, I. Guys, this is the moment of inertia about the neutral axis. We've been talking about it. Then, what about B? B in the denominator, this thing is the width of the cross-section. It is the width of the cross-section. All right? Now, this concept of width of the cross-section is interesting because I'm going to go back and ask you a question here. This is slide number 19. Everybody, please, take a look at slide number 19. Let's assume that Jonathan says B is the member width. That's correct. And sometimes some books use the letter T instead of B. It doesn't matter. It's no matter what they use, it is the width. All right? But tell me, for this inverted T section, if you were, and we will do it together in just a minute, but what would you use for the value of B, the width? What do you think? Ryan, I've been calling you Ryan. I'm not sure if that's correct, but if your name is pronounced different, tell me. But Ryan says 1. John Taylor says 4. Many of you are saying 1, and Mary says 4, and John says 4. Okay, guys. Now that I have your attention, let me explain. The answer is it depends. And Arash actually is giving me the right answer. He says you decide what the width is by looking at the section in which you're doing the calculation. He's absolutely correct. So what I said was the answer, what we use as B, it depends. It depends on what? It depends on where along the cross-section you are evaluating the shear stress. And that's what Arash is saying. Take a look, guys. If, for example, you see this red line? If you're calculating the shear stress at the neutral axis, you look and see what is the width at that level, at the neutral axis. It would be 1. So if you're calculating the shear stress at the neutral axis, you use B. You take B as 1. However, what if I come along and say, please find the shear stress at a section ½ an inch. See if I can draw a straight line here. ½ an inch from the bottom. ½ an inch from the bottom. What would you use as B? Well, in that case, B happens to be 4 inches. All right? So that's exactly what you need to do. because the shear stress value changes. It varies from the top all the way to the bottom. By definition, and now what I'm about to tell you, please write it down because this by itself could be a question. Shear stress at a free surface, either top or bottom, will be 0. All right? So shear stress in bending on a free surface, either top or bottom, will be 0. However, shear stress produced by bending has its maximum at the neutral axis. All right? All right, so the maximum shear stress occurs at the neutral axis. So if they ask you to find the maximum shear stress, automatically you have to identify where the neutral axis is, and whatever the B value, the width is at that section, that's what you use. Stephen is asking a good question. He says, what is the B value 1 inch from the bottom? And, well, that's an interesting question because if you pay attention, 1 inch from the bottom is the interface here. I don't know if you can see that green. That's the interface. So do we use a B of 4 or B of 1? Well, this part is highly theoretical, but Stephen, you use both actually, because at that level there are two levels of stress that act. One of them you use 4 to find it, and then you use 1. And there's an abrupt change of shear stress at that level. I don't think that level of theory is really that applicable to the exam. But Jeremiah is asking the same question. So, but that's what happens. All right. So there are two stresses at that level, and there's an abrupt change. All right. If you want to discuss that further, just send me an email. Now, let's go back to this. What about the value of Q? And remember, guys, I said earlier, some people have difficulty with this equation. Well, the difficulty that many people have is in calculating the value of Q, what we call Q. All right? If you go to a textbook or a reference book, they define Q as the first moment of the area. First moment of the area beyond the point that you're investigating. Which is, theoretically that's correct. But what I want to do is I'd like to go to slide 21. And yeah, Donald, you're correct. Your definition is correct. What I want to do is show this to you by doing the example. All right. So everybody, please pay attention because I know what I'm talking about. This value of Q has given a lot of people difficulty, but it's not a very difficult concept. Let's assume that we're finding the Q value. Let's say we're finding the shear stress at the neutral axis. So this is the neutral axis. The first thing that you do, you identify exactly where you're finding the stress. All right? That's step number 1. Step number 2, I want you to help me find the Q value associated with this section. This is what you do, guys. Let's take the area above that section. All right? Keep everything in perspective. We identify the section at which we are finding the shear stress. In this case, at the neutral axis. Step number 2, we are identifying the area above that point. All right, this is going to be this where I have highlighted red. Okay, now the next thing that I do, let's do a free body diagram of that area. And I have done that here. Do you mind moving your attention to this cross-section to the left? So what I have, this is the neutral axis, cross-section to the left, this free body diagram. This is the neutral axis, and the shaded blue area is that area that I just identified for you. You take that area, and then look what we do. Find the area. The area is 5.5 times 1. Does everybody follow what I got, how I got that? 5.5 times 1. 1 is the width. That's the area. Then I need to take that and multiply it by a moment arm. The moment arm in this case is 2.75. This is where things get complicated. How do we calculate the moment arm? Guys, I will tell you, and please write it down. This moment arm you need is simply the distance between the centroid of this area that we have highlighted, the distance between the centroid of the area we have highlighted, measured from the neutral axis of the entire body. So in this case, it's 2.75. Now, how do we calculate Q? We find the area, in this case 5.5 times 1 times 2.75, which is the moment area. I'm sorry, the moment arm. What do you come up with? Well, I come up with 15.12. That is indeed the answer. That is the Q associated with finding the shear stress at the neutral axis. Please note the units, inches cubed. Inches cubed. All right? Because there are 3 numbers we multiplied. Each one carries the unit of an inch. Now, let's go back to the previous slide. This is slide number 20. And I want you to please, if you don't mind, look at the bottom part of this slide. This is where we are calculating the shear stress at the neutral axis. Q is 15.12 inch cubed. I just told you exactly how we calculated that. So the equation is tau equals to VQ over IB. V is 2250. How did I get that? Go back to, I think it's slide number 19. Look at what is the maximum shear. Maximum shear in the shear diagram. You will see it's 2250 pounds. Times Q, Q is 1512. Divided by I times B. I is 97. And why am I using 1 for B? Because this is the shear stress at the neutral axis, and B happens to be 1. All right? Now, the second part of this problem says, could you please find the shear stress at a section 6 inches from the bottom? Mary is asking, is Q the absolute value? Yes, we don't need to have plus or minus signs. All right. Now, when we talk about, see if you can help me calculate this. When we talk about finding the shear stress 6 inches from the bottom, first, what did I say? The step number 1 is identify the location. All right. So it would be 6 inches from the bottom. Approximately would be there. What do we do next? Isolate the area above that section. Guys, I have done that here. So if you take a look at that, that is the area above the section at which I'm calculating the shear stress. Does everybody agree? All right? And if you look at the numbers, it comes out that way. It's 3 inches from that section to the top. Now, what I want you all to do, help me, and please go ahead and do it. I want you to calculate the Q value associated with this.